Comments, questions, observation, remarks? No, last time I was talking about
the rectifier and the boost as a regulator for after rectifier, more or less. And the
three letters. Give me three letters. PFC. Okay, and we saw what the PFC is used for in modern electronic systems. Power supply for the mains must appear for the mains as a resistance that takes undistorted current. It sinks undistorted current from the mains and with the current in phase with the voltage. If our load is non-linear, this load can generate harmonics, current harmonics, and these current harmonics are bad for the distribution system and for the neighbors. Because if you have harmonics taken from the mains, because your load is non-linear, there are diodes and capacitors, it's diode plus capacitor that makes the mess. If you have harmonics, we saw that the apparent power, that is what the electricity facility provider must pay for in terms of transmission line, transformers, generators, etc., equals V RMS times I RMS. And in this RMS current, there is both the 50 Hz or 60 Hz, whatever it is, the fundamental frequency, and all the harmonics. So you have a larger RMS current that makes your transmission line wasting power, heating up, it loads your transformers. But this is just a power that is apparent power. It's not the real, actual, true power. The active power is just given by VRMS. We suppose that voltage is sinusoidal, there are no harmonics on it, times the I1 RMS. I1 means first harmonic, the fundamental harmonic, the same frequency as the voltage, multiplied by the cosine of phi1. And phi1 is the displacement, is the angle between the voltage and current between the voltage and the first harmonic current the displacement angle. If our load looks like a resistance, it's not a resistance, because if we place a resistor over here, we invent the electric heating. But if it looks like a resistance, the active power is equal to the apparent power, because cosine of phi is 1, because in a resistor the voltage and current are in phase, and there are no harmonics. So the RMS current, the total RMS current, is just given by the first harmonic RMS current. The ratio between the active power and the apparent power is the power factor. And the power factor is composed by these I1 over RMS, this displacement factor, and this distortion factor. Distortion factor is I1 RMS and I RMS. We looked for a way, a solution, to have our power supply to appear like a resistance for the mains. And we saw that we have to use, we cannot get rid of them, rectifier, diode rectifier, bridge rectifier, usually rectifying the mains, and after the rectifier we get rectified waveform. So you take the negative half waves and you flip them on the positive side. We cannot place here a capacitor, because this capacitor and diode together make the impulsive current. And then we need some circuit, because to handle this voltage, because this voltage is absolutely not a DC. Yes, there is a DC component, but this voltage goes from 0 to 300 and some volts. And we saw that we started to look for a circuit, high efficiency circuit, so it means switch mode converter, that is able to take this voltage, this varying changing voltage, and to convert it to a constant DC voltage. We know three topologies by now, four, that are Buckboost, Buckboost, 2. So we say, okay, let's try to put here a buck converter in order to rectify this duck. Oh, now we have the converter. I said, we need a converter to get a DC component, so we started to try and use a buck converter, but a buck converter has an output voltage that is less than the input voltage. So, if we place at this level, for example, the output voltage, well, when the input voltage is high, we can step it down to the output voltage, but during the period close to the zero crossing model, during this period of time, we cannot have our buck converter boosting up the voltage from low level over here. We can decrease this dead time, this not working time, just decreasing the output voltage, but in this way, we get a very small duty cycle, active duty cycle, so it's not a good solution for the buck converter. Then we saw that if we, instead of a buck converter, we consider a boost converter, things are quite better, because a boost converter has an output voltage that is larger than the input voltage. So if we pick an output voltage that is larger than the peak voltage over here, no matter what is the input voltage, the boost is able to boost the voltage up. And if we are good enough, it's not easy, but it can be done, we can control the boost converter, we can convince the boost converter to send a sinusoidal current, or this kind of sinusoidal waveform. So we put here a boost converter, for example. We measure the voltage over here, and we control the boost converter in order to take an input current that is proportional to the voltage. We can get an input current that is something like this.
Two questions. The input capacitance, so we can put it, right? So
Get rid of it.
Okay. And the second one, if we want to have a constant voltage in output, in order to maintain the power supply, constant power in output, I expect that if we decrease, the input current have to be higher.
Okay. That is something you already asked me last time.
And more or less.
Yeah. Okay. You got me. Anyway, let me just go on a little bit more on this stuff. We can have any input voltage can be boosted up to the output voltage, and we can control, if we are good enough, we can convince, we can drive this boost converter to absorb a current disproportional to the voltage. Okay? That's good. Here, when we are close to the peak, we can go up by a smaller amount, because here we have something around 300 volts, 350 volts. And my output voltage, I don't want to have a too high output voltage. So for this kind of circuit, the output voltage is set around 380 volts, 400 volts maximum. So coming here and going up by a factor of 1.2, 1.5 is okay. But you remember that I told you the real practical boost converters cannot boost the voltage more than 3 or 4 times. Do you remember it? So what happens when I have here 30 volts? I have to boost the 30 volts up to 400 volts. That is a multiplication factor of 13. Can we do it? Can it make it? Yeah, it can make it. It's not very happy, but it can make it, because here current is very low. So if the current is very low, it means that the drops, voltage drop across the resistances and switches are not so important. So even if here it has to work with a very high boost factor, M factor, the fact that the current over here is very small, is 1/10, 1/13 of what is over here, makes me happy, because it means that it can, in any case, boost up with taking a small current, because I need just a small current at this point. I don't need the full current that I have to convert at this in the middle of the cycle. Okay? The problem is I have to convince, I have to control, I have to force, I have to drive, I am running out of verbs. This boost converter to sync exactly this red curve. Okay, it can be done. It's not trivial, but it can be done. What about, that is the second topology we have. What's the third topology we learned? Buck-boost converter has an output voltage that is opposite sign than the input voltage. So I could put here this output voltage for buck-boost. Does it work buck-boost as PFC? Yes, because any voltage you have over here, you can invert it down to this voltage. So a buck-boost is also a good candidate for PFC converter. What's the drawback of a boost converter? What's the drawback of a buck-boost converter? The drawback of a boost converter is that the output voltage is very high. The input voltage gets a peak of 350 volts or so. The output must be higher than that. And usually this output voltage is around 380 or 400 volts. A buck-boost converter has not this limitation. So a buck-boost converter could give you an output voltage that is, let's say, negative 50 volts, negative 100 volts. That is easier to handle than 400 volts that we get from a boost converter. Well, that's okay. You could say, oh, this is negative. Who cares? Because it's not a really big deal, because the PFC is just one circuit just after this rectifier, and then even if you have here negative and here positive, that's not the case with the boost. Even if you have here a negative and a positive, you say, okay, my reference voltage is this one, and this one will be my positive voltage. So it's not a big deal, because this is not connected to anything else. It's just a self-standing, independent. The problem of a buck-boost converter, if you use a buck-boost converter as a PFC, is that a buck-boost converter has a pulsating input current. It takes a pulsating input current, and the pulsating input current over here generates a lot of noise. Boost converter is better, because a boost converter has an inductor series input, so the input is cleaner, is more quiet than a buck-boost converter. Buck-boost converter can have very stressful and very noisy current at the input. So in general, people go for boost converter for a PFC. Okay? And if power is high means, let's say from 200 or 300 watts up, this boost converter is run in CCM, because CCM has less current stresses than DCM. Well, and now some transfer. This is my PFC. Let's suppose that is a boost converter. The input voltage B is something like this. Let me just repeat it over here. The input current must be, and we control the boost converter in order to get this input current, something like that. What's the instantaneous input power? Let's change color once more. What is the instantaneous input power? It's just the product of B times I. What's this product of these two waveforms?
It's not constant.
It's not constant. Not only it's not constant, but it goes to zero. No displaces, and it is something like this. Okay, I misaligned this zero, but it's just a sinusoidal function, or cosinusoidal function, or is the square of a sinusoidal function, basically. And this input power is not constant. Oops. Too bad. Too bad, because my load over here and my load over here would be another DC to DC converter that eventually isolates and supplies my final load. This DC to DC converter is taking from this output, from this section, from its input, is taking a constant power, because if the output load is constant, the input power will be constant. So we have this mismatch. Input power is going up and down because it has to look like a resistance, and the needed power is constant. So, if you look at many cycles, you can decide, you can tell me that the output power that you have over here, if we neglect efficiencies, the output power equals the average input power. Because you cannot cannot borrow power from nowhere. The output power is the average of the input power. If you average it on many cycles. But what happens in one single cycle? For one single cycle, you have a period of time over here when your input power is larger than what you need at the output, and just this part after, you have that your input power is less than what you need. But fortunately, this area equals this area. So, if you can store somewhere this extra, what is this, power versus time? Energy. If you take this energy, you store it somewhere, you have it available to fill in this lot of the power, input power, sometimes input power. Okay? So far so good? Okay, we look for energy storage. How can you store electric energy? Capacitor or inductor. Well, capacitors are far better to store energy than inductors. That means they are small for the same stored energy. Capacitors are smaller, less expensive, lighter, etc., etc. So, PFC circuits have here at the output a capacitor that must be there because it's a boost converter, so a boost converter needs this capacitor, but this capacitor is also used to control, to store energy and to release it shortly after it got the extra energy. So, how can you convince a capacitor to store energy and to release energy? What happens if you have a capacitor storing energy and releasing energy? Stress, sure, we have an AC current through it, but capacitors, our capacitors, are used to get stressed. What else? How can you convince a capacitor? What happens when you store energy in a capacitor and you release energy from the capacitor to the load? The voltage across the capacitor changes. When you charge the capacitor, voltage goes up. When you discharge the capacitor, you take the energy back. Capacitor voltage goes down. So, here, you will have, for sure, a voltage change, we call it ripple, a voltage variation, we call it ripple, that has the same frequency as the power that goes in and comes out. And this frequency is twice as much the input frequency. So, if we have a main that is at 50 Hertz, the voltage, this capacitor voltage, will go up and down with some ripple at 100 Hertz because it has to store and release the energy during this period of time and release it during this period of time. This output capacitor is the only case where I need to determine its capacitance. This output capacitor works as a energy storage at what frequency?
The input frequency.
Twice the input frequency, 100 Hertz. At 100 Hertz, any capacitor is a capacitor. We are still in the capacity area. So we need to determine the capacitance of this output capacitor in a PFC because we use it for storing energy at 100 Hertz or 120 Hertz or whatever it is, twice the line frequency. Well, it's easy because this is the input power, this instantaneous input power. The average output power is this, one half of it. This is a sinusoidal function. this area equals this area, because it's sinusoidal, I just shift it up. And this is my delta E, the change of energy that goes into and comes out from my capacitor. And in order to get this delta E, I need to allow to have on the output a delta V out. Voltage ripple at 100 Hz, that is what makes it possible to store energy and to get energy back, to retrieve the energy from the capacitor. I can define, I can impose what is my output voltage ripple. This time it is not a high frequency ripple, it's a 100 Hz ripple. And this ripple usually is taken in the range of more or less 10% or less of the output voltage. This delta V naught in a PFC usually more or less goes from, let's say, 20 volts up to 40 volts. 10% or 5 to 10% of the output voltage, something like that. And so I can now, knowing what is the delta E, knowing what is my delta V naught, I can determine how much is the capacitance, because this time is the only time that I need the real capacitance of an electrolytic capacitor. How much energy stored in a capacitor?
1/2 the
1/2
C times
Vc squared. Be careful, I don't want to store energy and remove all the energy from the capacitor. I want that my capacitor just has a small ripple, something like swinging up and down from 370 volts to 200. That is my ripple. So I will never deplete completely my capacitor. My capacitor will just have a small ripple, small variation of stored energy. So I cannot use this equation by itself. I cannot say, oh, I put here 30 volts and whatever is the ripple, etc. I need to differentiate this equation. Do you prefer to make engineering style calculations or mathematician style calculations? Engineering style?
Easier way.
Easiest way?
Easier way.
Easiest way is the engineering style. So that AC equals 1/2 C. Please don't write here delta EC squared, because this is a nonlinear function. This is V max squared minus V min squared. This is nonlinear. There is a square, so we cannot say just delta V squared. And that means that delta EC equals 1/2 times C naught. This C naught is what we are looking for. A squared minus B squared is something that you learned in middle school probably.
Square is on the
Sorry?
V max plus V times V max minus V.
A squared minus B squared equals A plus B times A minus B. So we have something like V max, V max plus V min multiplies V max minus V min. And so we have delta C. We know how much is delta C. It's just that area I was talking about. Delta C equals C naught times, what is V max plus V min over 2? V max plus V min over 2, what?
The output voltage.
Is the average output voltage. Is our 390 volts or whatever I told you. So this is the output voltage, the average output voltage that has a ripple on top of it. And what is V max minus V min? That's the ripple. Is that V out? And so this is very difficult because now we can solve for C, the output capacitor equals delta EC over delta V naught over V naught. We still need, we know, we decided 380 volts, for example. We know how much is delta V naught. We decided 20 volts, 30 volts, something like that. We still need to find out the delta EC, that is EC. Because remember the graph I drew a moment ago. This is the average input, the average output power, what you have to provide in the load. And here is the peak power, that is twice as much P out. Is 2 times P out equals P in E. And we have to find out how much is this area. How long is this base?
The half of time, the period of the sinusoidal.
Period of the sinusoidal, yes?
At 50 Hz.
Whatever it is, how much is this time? It's 1/2 of this period. How much is this period? From here to here?
20 milliseconds.
10 milliseconds. Because this sinusoidal frequency is twice as much because the second harmonic is the square of the input. So it's still times 1/2 of 1 over switching over line frequency. How much is this height? It's written on the
We have to compute the instantaneous power, the current times the voltage.
This is instantaneous power. What is it?
The third of P out multiplied by 2.
This is the P out, twice P out, P out multiplied by 2. This is P out, and so this height is just P out. It's the output power. So this height is P out. That means my input power, instantaneous input power, goes from twice as much what I needed to 0. And how much is this area? Don't start to integrate sine or cosine because you have to do it once in your life and then remember it. And that will be for sure less than base times height. So it will be 1/4 of the switching frequency, line frequency, times the height, that is P out, and then this is not a rectangle, this is a, what's the shape? Parabola. If it is a parabola, the coefficient is
2 over 3.
2/3. Come on, it's not a parabola. It comes from sine times sine square. A sine square cannot give you a parabola. A sine square gives you another sine, twice as much the frequency. This is a sinusoidal function. And so the coefficient for area of a sinusoidal function is similar to 2 over 3, but it's 2 over 5. Okay, this 2 and this 4 simplifies, and you get P out over 2 pi the line frequency. This is the energy divided by delta V divided by delta by V naught. You get your capacitance. The capacitance, the real capacitance, because it works, this capacitor works at 120 Hz if we are in the US, it works at 100 Hz if we are in Europe. This is one way to find out the capacitance value. There are different ways that are absolutely equivalent. Instead of talking about energy, power coming out from the PFC and going to the load. So the extra energy must be stored over here, lacking energy must come out from the capacitor. Instead of energy, you can talk about current. You can find out how much current comes out, and the current that comes out is proportional to the input power. If the voltage is almost constant, you can say, oh, I have a current that comes from here that is sinusoidal. All voltages by sinusoidal. I have a current that goes into my DC to DC converter that is basically constant, and so the extra current must go to the capacitor, it must come out from the capacitor. And instead of using either power and energy, you can use current and charge. It's exactly the same story. Or if you are a radio frequency guy, somebody that is a radio frequency guy over here, you can say, oh, the capacitor has a reactance. Here I am supplying this capacitor with an AC current. AC current goes completely through the capacitor, and V ripple equals I ripple multiplied by the capacitor impedance. What is the capacitor impedance in frequency domain? 1 over j omega c over j omega c. So you know the ripple, peak to peak value. You know the current ripple, you have to find it out coming out from here, peak to peak value. And you have omega. What is omega? 2 pi. The ripple frequency, that means 2 switch the frequency, the line frequency, and you get that's exactly the same. You get exactly the same result. Okay, did I answer to your question? That was his question. Well, are you happy? No. I am not, because the next subject that I will start in 10 minutes will be how to control a converter, any converter. And here we have the same problem. Here we have the input power, V in, and the input power will measure something like this. There is a voltage that is like that, there is a current that has the very same shape, and here we have an output power that is constant, because the output power that goes to the load is constant. The difference between this input power and this output power goes to charge the capacitor and come out from the capacitor. But I want to keep this output voltage more or less constant. Let's say around 380 ohms or so. That is a reasonable value. So I need a feedback system. We will go into the potential of this in a moment. I need a feedback system that measures the output voltage and controls the duty cycle to keep the output voltage constant. So here there is a controller, and this controller generates a duty cycle D to control my PFC. Okay, what happens if I try to keep this output voltage, because the controller is a stupid controller, or the designer who designed this controller is a stupid engineer. What happens if I, or the controller, or the designer who didn't take this class, tries to keep this output voltage constant? That is what you want. If I keep the output voltage constant over here, it means that I am trying to get out from my PFC a constant power. Output voltage constant means that the output power constant from here means that I am not storing or retrieving from the output capacitor in the end. It means that I have no ripple. I am trying to get from this circuit a constant output power while the input voltage is this one. Power looks like V times I. So if I force this output voltage to be constant, it means that I am forcing my circuit to deliver a constant power. Delivering a constant power means that it is taking from the input a constant power, and constant power means that V times I equals constant. This is the voltage. I can't do anything about it. What should be the shape of my input current to get a constant input power? It's just a reciprocal of this way. When the input voltage goes down, in order to keep constant power, the input current must skyrocket. And so my input current, so if the power has to be constant, it will be something like this. Does this red wafer look like a sinusoidal wafer? No way, not even by mistake. So, what does it mean? It means that my control circuit, my feedback system, must allow here some output voltage ripple. That output voltage ripple, which we determined a moment ago, that those 20 or 30 volts of output voltage ripple must be there. If they have no output voltage ripple, a PFC is not a PFC, cannot work as a PFC. So this feedback control system must not correct, must not stabilize the output voltage at 100 Hz frequency. The output voltage must stay more or less constant. I don't want my average output voltage go down to 200 volts or go up to 500 volts. I want that my output voltage stays around 400 volts, 380 or so. But I am forced, I want to have this output voltage some ripple, because this ripple is what makes the difference between a PFC and a standard DC to DC converter. PFCs have this output ripple, no way to make any story different, because the input power is going up and down, the output power is constant, and I need a ripple, period. No way to do it a different way. So, this feedback controller, this feedback system must check what is the output voltage over here. I want 380 volts, not 500 volts, otherwise I just fry all my circuits. But I don't want to correct, I don't want to stabilize, I don't want to control this output ripple. Output ripple is fine, okay? After you convince this controller to feed, to sense the output voltage, the DC output voltage, but not the ripple. Filter. What kind of a filter? Low pass filter. Well, a controller is a filter, basically. We will learn how to design these controllers. But what happens is that this feedback must be there for the DC and must not be there for 100 Hz. It means that the bandwidth of my control system, the bandwidth of my loop gain, the bandwidth of my return ratio, I don't know if you call it loop gain or return ratio, or fine. This bandwidth must be narrow, must be 10 Hz maximum. Because if the bandwidth over here is 10 Hz, it means that the DC goes through and I control the output voltage. But the output ripple that is at 100 Hz or more cannot go through this 10 Hz bandwidth system, and so the output ripple goes on undisturbed. And I need this, I don't want to correct the output ripple, because if I correct the output ripple, I get a non-sinusoidal input current. So, this feedback loop has a bandwidth, has a crossover frequency that is very small, 10 Hz or so. I told you many times that the boost converter is very difficult to control in CCM because it has a, let me tell you why, because it has a right F plane 0. And if you have a right F plane 0, you cannot control a system unless you go into crossover far before the right F plane 0. So, I really need a bandwidth that is 10 Hz. The crossover frequency will be 10 Hz. The right F plane 0 of this system would be 1 kHz, 2 kHz or so. And so, who cares about the uncontrollability of this boost converter? This boost converter is very nice, very well used in PFC circuit, because the bandwidth that I need is far smaller than the frequency what the right F plane 0 is. Okay, that's all. I cannot go into the detail on how this controller is made because we don't know yet how our controller is made in general. And now we can leave all this stuff and change subject and finding this razor. And let's go to the next subject. Next subject is an important one. And next subject is control of switch mode power. We learn how to design, how to determine stresses in a boost, in a buck boost, but we don't know how to control the duty cycle in order to keep dynamically control the duty cycle in order to keep the output voltage constant, or the input current sinusoidal or whatever. So we have here my switch mode converter. Switch mode converter has an output, let's say an output voltage. I want to keep this output voltage constant no matter what happens around this converter. This converter has an input voltage, 18. I need a control system that at least measures. This is my control system that measures the output voltage, compares the output voltage with the reference, and if the output voltage is not the right value that I want, what should the controller make? Adjust the duty cycle to keep the output voltage constant. So from here I will have a duty cycle output D that goes to control, to command the switch, and the output voltage will be constant, even if my input voltage changes, even if my load changes, etc., etc. This is a standard feedback system. We will learn how to design this controller. This is not the only way to make a feedback system. It's the simplest way, maybe, is the most immediate solution that can come to your mind. You want to keep the V naught constant, you measure V naught, you compare with the reference. If something is wrong, you change the controller, and the control is D, it's not the input voltage, the control is D, and you keep the output voltage constant. Very good. Feedback was invented since ever. The first time they started to analyze mathematically the feedback system was in 1800, I think, by Maxwell, and one of the equations. They started to analyze mathematically the regulators of steam machines. Because steam machines had problems to keep the speed, the rotation speed constant. They were oscillating, and so Maxwell started to work on this problem. But after engineers, they started to think about control problems. They came out with a different solution as well. Any other technique you know in control systems to control a plant? For a control guy, for a control engineer, this is called plant. For us, it's circuit, it's a power stage. Any other solution to control? I can read the output voltage and I use it. Okay, that's for sure, guaranteed that I will always read the output voltage.
Can read current, the output current.
We can read the output current. Yes, go think in a controlled way. Even if you read the output current, you cannot control the output current, because if you control the output current to stay constant, instead of having a voltage source, you get a current source. Yes, you had a control class for sure. Long time ago.
Check the stability.
We
can check the stability.
Check the stability. After, while you are designing this, But I am asking you about architectures, kind of system, methods of controlling. Did you ever heard about modern control techniques? What is modern control? Using a lot of matrices, using MATLAB, etc. No, this is not modern control. This is the tool to use modern control. Modern control means instead of measuring only the output voltage, you get more information and you can have better performances in your control system if you learn, you get information about all the state variables, not only the output. If you can sample, measure the state variables of your dynamic system, your control system becomes more performant. What are the state variables in a dynamic system, an electronic dynamic system? Voltages across capacitor. Oh, we have it here. The output voltage is the voltage across the output capacitor. And current with inductors. Here inside there is an inductor, at least one. So we can measure this current and feed it to the control system. And so we have a more performant control system, control technique, because we don't only know what is the output voltage, but we also measure the other state variable. And we can control the state variable. And when we add this extra piece of information fed to the control system, we talk about current. Current of control means measure both the output voltage and the current through inductor. If we only use this one, if we only sample the output voltage, we call it voltage mode control. Voltage mode and current mode will be the two techniques we will analyze very in detail in this class. There is more. And the idea is this one. Let's suppose that the input voltage changes. It happens. If the input voltage changes, it happens that this current value will change, the output voltage will change, and when I discover that the output voltage has changed, I say, oh, I have to take action, and if the output voltage is changing because the input voltage changed, I have to change the duty cycle to keep the output voltage constant. That is a standard feedback system. But if you wait until the output voltage moves to take action, you are late because all your state variables have been screwed up. Your inductor current has changed, the capacitor voltage starts to change, at that point you say, oh, something is happening, let me correct. Too late, could be, for some control systems. So, there was another technique that was something like this. You measure the input voltage, you also feed the input voltage information to the controller, and if the input voltage increases, instead of waiting that this increase makes the current through inductor to go up and the output voltage to go up, as soon as I see that the input voltage changes, the input voltage, for example, increases, immediately the control system decreases the duty cycle in order to keep the output voltage constant. This technique is called voltage feedforward. And if you go chronologically in with the historical mind, the first control that was used was the voltage mode, because the straightforward idea. I want to control the output voltage, I want to keep it constant. I measure it, and the controller changes the duty cycle to keep it constant. The second that came in the story of these control systems was the voltage feedforward. And the third one that was invented by mistake by a non-control engineer, fortunately, we will see why. The third technique was the current mode control. If you use a current mode control, automatically includes in itself also the voltage feedforward. So if you use a current mode control, you don't need a voltage feedforward anymore. So voltage feedforward is not used nowadays too much. Actually, it's quite rare to use it because a current mode is a very powerful control system, control mode, and it includes the advantages of voltage feedforward. So this is just a drop out of the use. I am designing these days a system with a PFC and with a DC to DC converter, and for some reason, for some weird reason, I would consider